One small step for man, and one giant leap for mankind. These are the famous words of Neil Armstrong when he took his first step on the moon, which will forever be remembered. The developments made in the space exploration industry the last number of years are both exciting and inspiring. In this webinar today, we will be exploring some of the most innovative technology of the 20th century. We will look into what it takes and what is needed to simulate the complex rocket propulsion systems of today, and which essentially put the first humans on the moon 53 years ago. Today, it's also intricately designed to be reused for several launches. So I hope that you will find this webinar interesting and insightful, and that it will spark your passion for space travel. My name is Leander Klein, and I am one of the technical pre-sales engineers here at Flownex Simulation Environment. My background is mainly in power cycles, renewable energy, as well as propulsion systems. Essentially the type of engine that we'll be investigating today is more specifically a liquid cryogenic rocket engine. Okay, so for today's webinar, we will look into a brief overview of different cycle designs, whereafter we will discuss the RS-25 liquid fuel rocket engine. Flownex will then be introduced, and we will see how Flownex can be used in the design and development stages of these rocket engines. A simple live demonstration in Flownex will then be presented, and the full RS-25 rocket model will be demonstrated with full transient behavior and control systems included. So first of all, rocket engine cycle designs. Liquid-fueled rocket engines have come a long way since the first one launched by Robert Goddard on March 16th, 1926. To today's more sophisticated rockets such as the Raptor engine of SpaceX. Different rocket cycles have been investigated and designed, each having their own strength and purpose. The gas generator cycle, also known as the open cycle, pumps the fuel and oxidizer into the combustion chamber using a turbo pump. Just enough oxidizer and fuel are branched off from the main feed to a pre-burner where the combustion takes place. The off gas from this combustion process is then used to propel the turbine side of the turbo pump, which is then connected to the pump side with a shaft. The pump side of the turbo pump are then used to pump the fuel and oxidizer. The products of the combustion process in the pre-burner is then ejected into the atmosphere. This makes this cycle less efficient because the fuel and oxidizer used in the pre-burner is essentially wasted. With this type of cycle, it's more suitable for when fuel such as RP1 or rocket propellant 1 is used. When using fuel such as RP1, the products of the pre-burner contains a black sooty substance. This substance is created due to incomplete combustion resulting from the fuel being burnt at lower temperatures. The low combustion temperatures is essentially necessary to ensure that the temperature limit of the materials used in the combustion chamber is not exceeded, and it's essentially achieved by slightly reducing the oxygen supply. In other words, the pre-burner is being run fuel-rich. However, when the combustion process in the pre-burner is fuel-rich, there will be unburned fuel which appears as dark clouds of soot. The unburned carbon molecules are essentially at a high pressure and will bond and form polymers in a process called coking. The soot created in the coking process will then stick to everything in its path. The soot can damage components in the rocket, and this can then be the reason that it is ejected to the atmosphere. But rejecting the combustion products of the preburner makes the cycle less efficient. Can we not then use these products and reintroduce them into the system itself, and doing this increasing the efficiency? This idea led to the creation of the closed or oxygen-rich cycle. The problem is, however, that when redirecting the sooty gases into the combustion chamber, it will clog up and break the injectors and all the components in its path. To avoid this problem in the cycle, all the oxidizer is sent through the preburner. The combustion products of the oxidizer-rich reaction do not contain soot, which then does not damage the components in the rocket. The oxidizer-rich products are then reintroduced into the combustion chamber, where the main oxidizer is combusted with the fuel. This solves the problem with the clogging and damage to the injectors and components. The problem is now that, however, that using all the oxidizer will result in a very high temperature oxidizer-rich combustion products, which will essentially damage most materials. And this means that specialized and expensive materials are needed for this rocket design to withstand these temperatures. A cycle was then developed in an attempt to create a closed-loop cycle with lower temperature combustion products, a closed fuel-rich dual-shaft cycle. This cycle uses a fuel-rich combustion process in the preburner, and to avoid the getting sooty off gases, the fuel used now was hydrogen, which resulted only in water as a product. In this cycle, we have two preburners, one used to propel the fuel turbopump and one to propel the oxidizer turbopump. All of the fuel and essentially just enough oxidizer are pumped through the preburners, resulting in fuel-rich combustion products, which is then sent to the main combustion chamber, where it is combusted with the rest of the oxygen. This cycle addresses the issues with high temperature oxidizer-rich products, but due to the low density of hydrogen and the possibility of an explosion when the fuel-rich off-gas slips to the oxidizer side of the oxidizer turbopump, very specialized seals had to be developed. To essentially address this problem, another closed cycle was developed called the full flow cycle, where the fuel turbopump ran fuel-rich and the oxidizer turbopump ran oxygen-rich. The only difficulties now were, of course, the extreme hot oxygen-rich off-gases, where specialized materials were needed once more. The products of both of the preburners are then essentially sent to the main combustion chamber, where the fuel-rich and oxidizer-rich products are then combusted. These products are already at a very high temperature and pressure, resulting in much better combustion process. The different cycles have been used and having different strengths and weaknesses. We will now look at one of the closed fuel-rich dual-shaft cycles called the RS-25 rocket engine. So one of the more complex rockets that has been developed is Aerojet's Rocketdyne's RS-25 liquid cryogenic rocket engine, used as the first stage propulsion system for NASA space shuttle, and now the space launch system, also known as the SLS. This rocket uses liquid cryogenic hydrogen and oxygen as the fuel and oxidizer. Rated at approximately 491,000 pounds of thrust at its nominal power level, it essentially packs quite a punch. The original engine can be tracked back to the 1960s, with development starting in the 1970s. The first flight for this rocket engine was for the STS-1 program on 12 April 1981. Since then, this engine has had several upgrades and improvements with regards to safety and performance as well. This engine produces a specific impulse of 366 seconds at sea level and 452 seconds in a vacuum. It weighs around 3.5 tons and can be adjusted between 67 and 109% of its rated power level. The temperature in this rocket can range between minus 253 to 3,300 degrees Celsius. The extreme cold temperatures are due to the hydrogen and oxygen that needs to be liquefied so that it has a smaller volume to fit into tanks that will be transported with the payload. Hydrogen liquefies at a temperature roughly below minus 253 degrees Celsius, where oxygen liquefies below minus 183 degrees Celsius. And this essentially means that oxygen and hydrogen need to be cooled down on site into cryogenic or very cold temperatures and just before launch be fitted onto the vehicle. For the space shuttle, 3 of the RS-25 engines were clustered together, connected to the orbiter, where the fuel was drawn from the external tank. These engines were used to produce thrust for the entire ascent, with additional thrust being added by 2 solid rocket boosted engines for the first 2 minutes of the launch. 4 RS-25 rocket engines are proposed for the Space Launch System in a similar setup than that of the Space Shuttle. A diagram of the RS-25 rocket engine is shown here. At the top left-hand side, liquid cryogenic hydrogen is sucked in by the low-pressure fuel turbopump, which then feeds it to a high-pressure fuel turbopump. It then gets split into 3 separate branches. The lower branch is sent to the nozzle, where it is used for cooling purposes. This helps to ensure that the material do not increase to a temperature that is higher than its limit. While cooling the nozzle, this hydrogen is also then heated into a gas form, where it is then sent to 2 pre-burners. The middle branch is directed to the main combustion chamber, where it is also used for cooling. This stream is then essentially used to drive the low pressure turbopump. The upper branch is used to control temperatures of hydrogen moving to the pre-burners itself. On the upper right-hand side, liquid cryogenic oxygen enters at the low-pressure oxidizer turbopump and is then also sent to a high-pressure turbopump. After the turbopump, some of the hydrogen is tapped off to drive the low-pressure turbopump, and another branch exists which supplies the 2 pre-burners with oxygen. The amount of oxygen sent to the pre-burners will determine the output of the high-pressure turbopumps, which will then affect the flow rate of the hydrogen and oxygen, and then ultimately affect the thrust of the engine itself. In essence, the throttle control is accomplished by adjusting the flow rate of the oxygen to the pre-burners, and essentially the rest of the oxygen will, which is not branched off, will then be sent directly to the main combustion chamber. The combustion process in the pre-burners will result in fuel-rich combustion products, which are then directed into the or to the main combustion chamber, where the rest of the fuel will be burned with the oxygen directed to the chamber. The combustion products in the main combustion chamber will then be accelerated in the nozzle, creating thrust. So essentially, this can be seen by this animation. This essentially shows the complexities and interdependencies of such a system. For example, when reducing the oxygen to the pre-burners, the turbo pump speed will decrease, which will then decrease the flow rate of the fuel or oxygen, which then will decrease the fuel and oxidizer to the pre-burners and reduce the flow rate to the main combustion chamber, and then ultimately reduce the thrust. In essence, the entire system is strongly interdependent, which makes such a system extremely difficult to simulate using three-dimensional computational fluid dynamics software. So, what would be needed to simulate a large interconnected system such as the RS-25 rocket engine? First of all, you would need to use a simulation software package that can give you the capability to use different fluids, such as gases, liquids, and mixtures. It should also be able to include the ability to evaluate the properties of cryogenic fluids, and should have the ability to create custom fluids as well. Pressure drop components should also be readily available to ensure that the simulation model replicates the true characteristics of a system. And this can include things such as piping, valves, bends, and so on. Turbo pumps should also be modeled, allowing for speed and power calculations for different conditions. And another important aspect for such a system would be to implement a control system. And this is just to ensure that such a system shows the same behavior transiently than it would in real life. Different heat transfer models would also need to be needed, such as a conduction, convection, and radiation. There are essentially multiple complex heat transfer occurring in the RS-25 engine. For example, radiative heat transfer from the combustion processes onto the inner material of the nozzle, radiative and convection heat transfer of the external body to the environment, and a couple of more heat transfer as well. The combustion process should also essentially be a model. This model should represent a real combustion process and be able to produce the products or components in the product of the process, as well as the flame temperature, to ensure that correct heat transfer is calculated. Finally, such a model should also be able to model the acceleration of gases in a nozzle for subsonic and supersonic flow, and calculate the thrust that would result for a certain condition. So increasingly, it has become more important to evaluate cycles such as the RS-25 as fast as possible. However, when the complexities of the rocket engine are taken into consideration, 3D CFD analysis is just not a viable option. So simulating the system components of the rocket engine in its entirety is important to understand how all these components will interact with each other and how the system will perform at different operating conditions. Changing parameters in the system and assessing the impact on the performance is tedious using 3D CFD software, and could take weeks for each iteration to complete. So this is where Flownex has gained popularity. Flownex is the industry leader in 1D CFD software, allowing for the system simulation of large interconnected thermal fluid systems, capable of fast transients and steady state solving times, and introducing the ability for rapid system cycle design iterations. Flownex has been used extensively for R&D purposes where 3D CFD just cannot compete. Flownex uses fundamental physics and theory from leading research to solve some of the world's most complex thermal system problems. Flownex is essentially an engineering tool that can be used by engineers in the design and analysis process of thermal fluid systems. It solves the fundamental physics for flow and heat transfer components of large thermal fluid systems. Flownex houses a large library of standard components used in industry, advanced fluid models, control library, and integration with third-party software such as ANSYS, MATLAB, and Simulink. Ensuring for the best standards of quality compliance, Flownex is developed within an NQA1 and an ISO 9001 environment. Flownex also has a user-friendly interface with a help manual conveniently accessed through using the F1 button. As I said, Flownex uses a one-dimensional approach in solving systems. Flownex does this by solving the conservation equations of mass, momentum, and energy on component level. All components can essentially then be solved fundamentally in true steady state as well as transient with either fixed or adaptive time steps. So in summary, Flownex can be used to run steady state and transient simulations where flow is predominantly in one direction and with heat transfer essentially in two dimensions. It simulates system behavior from physics on component level. So this brings me back to the typical requirements for such a large interconnected thermal fluid system and how Flownex can be used in the design and modeling of such systems. So what capabilities does Flownex provide the user in the simulation of such systems? Well, Flownex gives you several fluid models such as liquids, gases, mixtures, and two-phase fluids. It also allows you to create your own custom fluid and allows for the evaluation of cryogenic fluid properties. Flownex contains a large library of standard pressure drop components found in most industrial applications. This essentially includes components such as piping, bends, valves, and so on. Custom pressure drop models can also be created in Flownex if needed, and coupling to third-party software such as ANSYS Fluent for specific custom complex geometry can also be done. Flownex also gives you the ability to model turbines, compressors, and pumps. These components can either be used with a specific manufacturing data provided or can be used in the design process to find the appropriate pump or turbine. Flownex also provides the user with the ability to create turbopumps by connecting a turbine and pump with a shaft. For this case, Flownex allows for advanced power matching between multiple turbines and pumps as well. You also have the ability to add in control systems. The user has the ability to add in control models such as a PID controller, analog and digital. This allows the user to understand true transient control behavior of a system. And Flownex also allows for several heat transfer models provided to essentially ensure that all the heat transferring phenomena are realized. And this includes models for convection, radiation, and conduction as well. Heat transfer models such as a plate heat and fin tube heat exchangers are also included in Flownex. And then for combustion, a CEA adiabatic flame element can be used to calculate the off-gas composition and maximum temperature for a chemical reaction of a chemical mixture, and using the NASA Glenn chemical equation program, also known as CEA2. And then lastly, Flownex also allows for calculating the thrust for a nozzle found in rocket engines. The exit thrust nozzle can be used to model subsonic as well as supersonic flow at the outlet of a flow network with gases and superheated fluids. Now that we have discussed the complexities of modeling a liquid rocket engine and how Flownex can provide the user the ability to solve such systems, I will now show you a live demonstration on how to model a basic combustion network in Flownex. And after this, we will look into the full system model of the RS-25 in Flownex itself. Okay, so we are in the landing page of Flownex simulation environment, and just to give you a quick overview of how essentially it looks, you would essentially have different ribbons here at the top for different options in Flownex. At the left-hand side would be a properties window for components, viewing your inputs and results once selected. And then at the bottom, we have our flow solver conversions, showing you how converged your results are according to the convergence criteria that you have specified. On the right-hand side, we have multiple inputs, or essentially components that you can use in the library. And then there's a few other options on the solver itself and so on. So for today's demo, we are going to look at how to essentially create a basic combustion process, which can typically be found in a rocket engine. And this would consist out of everything from the hydrogen and oxygen flow paths, where it gets combined and then combusted, and then essentially how it is expanded or accelerated through the nozzle, creating a certain thrust for the rocket engine. So this is typically what we would see in a liquid rocket engine. So first of all, let's start with boundary conditions. So we will have two paths. One boundary condition will be for the inlet of the hydrogen and the other for the oxygen. And for this case, we'll just use flow resistance components. And let's just say that for the hydrogen, would be essentially at the top. Let's just note it down, hydrogen, so that we do not get confused later on in the simulation. And then we do have oxygen right here. And then for the inlet boundary conditions, let's put hydrogen as for its temperature or for its pressure. Okay, no, we won't specify the pressure here. We will specify the temperature being 222 degrees Celsius, and then a mass flow of, let's start with 200 kilograms per second. Then for oxygen, we'll use a temperature of 222 degrees Celsius, and then a mass source. So we're essentially fixing the mass source at the inlet here of 700 kilograms per second. Then we'll define the admittance for this flow resistance. So I mean, this is just a custom pressure loss model, but it's just to represent the flow of the two branches. We can then copy over this these flow resistances and then join it here. So essentially we would have these two flows and it would essentially join. And then let's add in another few flow resistances. I'll show you in a moment why this is necessary. And then of course a exit boundary condition, and in this case we'll just define it as a pressure boundary condition of 100 kPa. And then next we need to define the fluid being used in this demo network. So I've already created a mixed fluid consisting, so this is just for an example, consisting out of hydrogen, water and oxygen, and that's typically what we'll see for the entire combustion process. We can of course add in more elements if needed, but for this demo this should be sufficient. And then we can add this fluid to the network. So we'll go to mixed fluids, propellant mixture, and we should be able to solve by now. And there we go. We can also just tidy up this up a little bit. And let's then just evaluate on some of these nodes. For example, you would be able to see the mole fraction. Of course, we have not included the mass fraction at the inlet. So let's just define that here on the boundary. So we have to assign the mass fractions for each inlet of that specific for that specific fluid. So we'll add it oxygen here and hydrogen at the other side, and then we'll see that we have a certain mass fraction at each node. So let's also just quickly drag in the hydrogen, oxygen, and sorry, not the oxygen, water and then oxygen. And let's create our own caption here, being hydrogen, and this will be the H2O, and here we have oxygen. Okay, and we can align these. And let's do the same for this node right here. We can drag in. So what we can rather do, we can copy this over to here and then drag in these values and just overwrite them. And this in such a way we are saving a little bit of time to essentially recreate the format of these labels. And we can then just have equal spacing, but of course we can make it neater at the later stage. Okay, we can solve again. You will have no issues there. What we can do now is we can add in a combustion process. So we can find this at the chemicals reaction branch, the CEA adiabatic flame, and we can connect it up such that it links up on the node before and after a flow resistance. And what we can see now is, let's also just drag in the temperatures and another temperature here. So of course the temperatures are the same before and after, as there's no, we haven't solved this network yet. So what we would do is, once this has solved, we should see a change in temperature as well as a change in the mass fractions. Okay, so there you can see the temperature has risen to 2520 degrees Celsius, and we have used quite a lot of our oxygen and hydrogen. You can see we have quite a few left, or a large mass fraction of hydrogen, and a lot of water vapor has been created as a product in this combustion process. So we can then accelerate this hot gas products through a nozzle, similar that what you would find in a liquid rocket engine, with using one of these discharge nozzles called the exit thrust nozzle. And we will just link it up in this manner. And we can then let's specify the area. And this would, of course, be dependent on your specific geometry, but we'll just use this as an example. And we can then drag in the thrust that is being calculated by Flownex. And here you would see essentially this is the thrust being calculated for this specific condition. So what we can then do is we can add in maybe a line graph. So what I want to evaluate is the thrust being calculated. And then, of course, what I want to change in this system is the output pressure. So this would give you a rough idea. As a liquid rocket engine is ascending into the atmosphere, the atmospheric pressure would change, and this would affect your thrust, and we would be able to see it in a transient simulation. So let's change the minimum and maximums for this track bar to 100, between 10 kPas and 100 kPas. Let's solve it again, steady state, and then essentially in transient, and then you can see it is being calculated here, the thrust of this nozzle, and we can then change the outlet pressure, or in this case the atmospheric pressure, and you would see how Flownex can essentially then calculate the thrust for different exit pressures. So this just gives you a basic idea of how you would be able to implement Flownex in your for combustion process, for very basic nozzle combustion system, and then essentially calculating the thrust for a rocket engine. Very similar to what we would see in a RS-25 rocket engine. And essentially, we will now have a look at the full RS-25 rocket engine. But this essentially just shows you a very basic modeling process. This is essentially the entire RS-25 rocket engine being modeled using different components in Flownex, and it's from its standard components in the library. And so essentially this is the inlet for the hydrogen, Here's the low pressure turbo pump being created from a pump, a shaft, and turbine component. And then this branch is essentially fed to a high pressure turbo pump, and this flow is essentially branched to 3 different branches. One going directly to the nozzle. You can see this is the nozzle itself, being used for cooling purposes. So here there's a combustion process going on. There's some hot gases, and this radiative heat is being transferred to the material, and the cold fuel is being used to essentially help with the cooling of this material as well. Then we have a different branch going to the nozzle, and another branch being tapped off directly to the pre-burners, fueling these pre-burners. So you can see that right here. The branch going through the nozzle also goes to essentially propel the turbine side of the turbo pump here at the low pressure turbo pump, and then is being fed back into the main combustion chamber. And then we have a similar setup for the oxygen side, where we have a low pressure turbo pump that is being fed to a high pressure turbo pump. And interesting here, we do have multiple pumps and one turbine, simulating this turbo pump right here. And we have some complex power matching going on right here. And then one of this is being branched off. The flow is being branched off. One being to propel this the low pressure turbo pump, and then the other. There's a portion going into the main combustion chamber, and one to the essentially back to the pre-burners. And essentially this flow to the pre-burners, this oxygen flow to the pre-burners, are how this RS-25 are being controlled. So the valves to the pre-burners regulating the oxygen can be adjusted to, and this would essentially affect the entire system, and then ultimately your thrust of this rocket engine. So let's just solve it steady state, and what we will use today is the non-iterative solver that has been released in the new Flownex release of 8.14, and essentially this will allow us to simulate larger systems in a faster time. So let's start running it transiently, and you can see here how the speed of each of the shaft here, the turbo pumps, changes as it's seeking equilibrium, and we can see the thrust being calculated at the lower left hand side. And what I've added in here in this model is a script that essentially calculates your kinematic equations, taking the thrust into account, and then essentially calculating the distance from sea level, the velocity, and then also using these parameters to change the outlet pressure. You can see it is reducing as your rocket is essentially ascending through the atmosphere. So you can see here on the right hand side that the velocity and distance being calculated, and this essentially, such a model will enable the engineer to get a better understanding of how this engine works, and also how it would perform to changes in the system itself. So basically you can also then change the valve lift and see how that would essentially affect your thrust. You can see the effect of that valve being closed affects your thrust, And essentially simulating the entire system interdependently in Flownex would give you a overall view of such a system, and you would be able to connect it maybe to different softwares where this information might be quite useful, or even use it for different cycle designs. There's actually quite a few options available for using Flownex for such systems. And also, this is a very high-level simulation of the RS-25 rocket engine. Of course, you can start zooming in and actually simulating smaller and smaller parts in more detail, depending on your specific thermal fluid case. Okay, so essentially, Flownex gives the user the capability to simulate and design large interconnected systems such as the RS-25 rocket engine. The CFD approach of Flownex allows for reduced simulation times and is capable of solving systems for which 3D CFD software cannot really compare. Flownex can simulate real-time transient responses of complex systems, giving accurate scenario-based information for the user using it. Flownex provides all the needed capabilities to model liquid rocket engines, including several fluid capabilities, pressure drop components, turbo pumps, control systems, heat transfer models, combustion process modeling, and thrust calculations. And this brings me to the end of this webinar. I hope that you have found this webinar to be insightful. If you have any inquiries or just want to reach out to us, just send an email to sales@flownex.com. Alternatively, you can have a look at our website for more details on Flownex and its applications. Have a great day.